Okay, 7:30, let's get started. So we have our project one due tonight. Hopefully, most of you or all of you have done your part, including the report writing. I see there are already some submissions on this part, about 20. Okay, that's good. So keep it coming. Uh, And thanks, Jerry, for sharing your finding on the Intel model sim, that tool. That's very good. Like, in fact, today afternoon, I was looking for alternate different tools, and one of them was this. I'll try it maybe over this weekend, but since you have tried it, right, already?
Yeah, I've been using it for my project one so far, just as a replacement, like last
Okay,
minute.
okay, that's good. That's good. So whoever is struggling till now, if there is any with the installation of the model sim or any other simulator, maybe you can look at the discussion post by Jerry on our project one discussion. He has given the link. You have given the link, right, Jerry, to that download of the model sim?
Yeah, it should be in the reply to it.
Okay, okay, good. Thank you very much. Yeah. So that would be an alternate. There is another tool I am trying to evaluate and see how effective is that. That is from the Aldec, another company. It's called Active HTL. Seems like there is a student free version of that. I'll also play with that maybe over the weekend and see how effective is that. But if Intel's models in work, that would be great. What is going on in the model sim like mentor, which is previously mentor, it is now officially merged with the Siemens, which is a big giant enterprise software corporation, and every policies and installation and all these things are changed suddenly this year during this time. And that's why if you go to the free link of the model sim PE edition, you'll see there is some grant page and things like that. It seems like it is for the teachers to apply for a grant and take the license and stuff like this. Being myself as a Siemens employee, I'm trying to get hold of a salesperson directly and talk to them to see what is going on and what is alternative. However, if the Intel's that FPGA model sim integration works, that's great. Please give it a try if someone hasn't tried that yet. With that respect, let me do a quick poll about this simulation tool. You can take it anonymously. Basically, it is asking what's your working simulation tool that you have used to simulate design and lab successfully. So please take a moment to respond to that. Maybe in a minute, we'll close it. Okay, 35 of 37, maybe another 20 seconds, I will keep it open. Okay, I think this is good enough pulse. So here the shared results. So most of you, 29 of you are using model sim, great. There are a couple using the Xilinx ISE as an alternate tool. For those who are using Xilinx ISE for project one, it should be okay. Today I found out that Xilinx ISE is not supporting some of the Verilog macro construct, like a write memory and stuff like that, which is needed in the project two, or which is useful in the project two. So for those, I would like to suggest that try the alternate, that the one that Jerry suggested from the Intel model sim. Try to have it. Try that out. Xilinx ISE simulator, that simulator doesn't, seems like it is not supporting some of the Verilog construct. So we'll come back to that. I'll try with the Aldec simulator as well and see how it goes. But try that there is solution there. Uh, for others, someone has not installed yet. Please work on that. I was expecting that you already installed and keep on working on the labs. Maybe other situation happens. I don't know. Like, I'm not blaming you for those things. Have installed but not tried. Okay, these one, like if you have installed model sim, like compilation wise it would be fine, but if you have problem with the license installation, then you cannot simulate. So please make sure you can simulate in your environment. And now, since it is this all these complex things to merger with the Siemens from the mentor is happening, grabbing the license, I don't think it's going to be easier. I'm trying to find out internally from Siemens, but let's see uh, what happens there.
Professor,
Yes, nothing.
Is Jerry's solution in the discussions somewhere?
Yes, project one discussion, I believe. Jerry,
Okay.
right? Project one discussion.
Yes, the Intel FPGA. It also supports Linux, I've heard.
Oh, okay. I'll
Okay,
try
thanks.
Linux. Yeah, I have a Linux installation. I'll try it out.
Professor,
Yes.
I had a question for the project.
Yeah.
The report, what's the threshold that we can't exceed
Threshold for what?
for the report when you compare it to the other reports?
Yeah, it's already in the assignment. I think it's 25%.
So if we're at 25%, is that acceptable?
I think so. Yeah.
So just to make sure, because mine's is 25%, that's why I'm asking.
Okay. Well, yeah, I think 25% should be okay.
And
usually
then
when I view, usually it differs. It basically comes down actually, not goes up. So when I view as a teacher view, like I can analyze like more granular levels. So don't worry. If it is 25%, I think you should be okay.
Okay, thank you, Professor.
Okay. Now, oh, someone said other in that poll. Is that Jerry? Is that you? You're saying other on the Intel thing?
No, I put Model Sim
Okay.
because the Intel version of Model Sim is the exact same version. It's also more updated too.
That's what I heard also, like I saw in the web. For whoever is answered other, can you please elaborate what are you using as a Verilog simulator? If you want to, it is voluntary, like it's fine. If you don't want to, that's fine as well. Okay, all right. Let's move on. So, any question from any of you on the project or the one that we want to be discussed, like lecture 7? That's what you're supposed to cover up tonight. So, any question on those topics or previous topics? Where's the module 3? No, there is nothing on the module 3 discussion. So, all right. Since you guys don't have question, let us do some explanation through the Verilog simulation. Let's do this screen one. Share. So remember, we were discussing about a NAND-based storage element called S bar R bar latch, and we were we're actually trying to understand the functionality of this latch, what it does. There is some set condition, reset condition, and hold condition, and also undefined conditions there. How about we put this similar logic circuit in the simulation environment and simulate and try to understand in terms of simulation and in terms of waveform how it goes there. So uh, where is my model? Okay. I have some already predefined code here. Okay, and okay, so this one S bar R bar latch, this one exactly corresponds to this circuit, this one. So what I did, I basically oops. Okay, so I did instantiate two NANDs and did a Q, here Q coming to the input of the other NAND. So you see that instantiation of the NAND 2 is driven by Q, and instantiation of NAND 1 is driven by the Q bar. Q bar goes to another NAND. And other two inputs are basically S bar, R bar. So that's what the very simple Verilog logic gate level description would be, with the input and output being S bar, R bar, and output being Q and Q bar. And then I have some test bench around that, S bar, R bar, latch to B. What it does, it starts with S bar 0 and R bar 1, which is a set condition, here, right? And then it goes to on hold, which is like 1 1 here. Hold is a 1 1 is a hold condition. And then we go to some reset condition by setting S bar to 1 and R bar to 0. Then also hold, and then after 5 nanoseconds, we stop the simulation. So let's compile it and then bring out the project library, S bar, R bar, latch test bench. Let's simulate that one. Double click on these. Okay. So yeah, let's look at how that instance look like, this S bar, R bar instance. Right. And here. Okay, just two simple NAND, one is driving another. So this is a feedback loop going on between them and is driven by the R bar and S bar. And here is the instantiation of that Verilog module. We define that module as S bar R bar latch. We instantiate that S bar R bar latch as an S bar R bar instance 01. And some register is driving S bar R bar, driving their input. And on the where we are looking at the output. We are observing the output from that instantiation of that logic gate. So let's put these three under our wave observation. So these are my, maybe I'll just get it out. Okay. And then we simulate. Okay. Where is my, okay, now. Maybe a little bit off. Okay, this is good. This is good. So you see at this point, my S bar is 0, R bar is 1, which is exactly the set condition. Means my Q supposed to be at 1. And Q bar is, of course, the inversion logic of that. So Q bar is 0. Now, so this is my set. So I am setting the logic, the output here to be 1 from the Q. And then at this time point, I went into the hold. Means I set the both S bar, R bar as 1, and my output does not change. My Q output is still 1, and my Q bar is still 0. I'm holding on to that. So as long as I'm keeping the input logic of the S bar and R bar keeping to it 1, I just holding the previous set value. Previously I set 1, I'm keeping hold on to that. Now at some point of time, I reset it, like at the 10 nanosecond, I went to the reset logic, like here, with S bar 1, R bar to 0, which brings the Q to 0. See, brings the Q to 0 and Q bar to 1. And after that, I make it into the hold condition, 1, 1 again. And now you see the Q to 0 and Q bar to 1 is being held. Like as long as now from this time onward, as long as I'm keeping these logic value to S bar and R bar as 1, 1, I am going to have the value 0 at the Q out. So that's what is meant by storing a logic inside a storage element. Like initially you'd think, hey, this is a logic operation, right? One is driving another, we know how it is evaluated. But overall conceptual level, this becomes the fundamental block of storing a logic value, logic element, right? Question on this conception so far? Okay, now we move on to the next one, right? We take this one and then have something a little bit complicated, introduce two more NAND there with a control, meaning that if the control or C logic is 0, it's a hold condition. No matter you are changing what you are changing, and then S bar or S and R terminal, your output Q is not going to change at all. It will just being held to the previous value what Qt was. Like if Qt was 0 at that time point, next time point you probe it, it will remain 0. No matter what the S and R logic values are in between that time. Similarly, if it was held to 1, it will be held to 1 no matter what the S and R values are there. And if now C is 1, if we see C to 1, then with a set 0, set 1, reset 0, that will bring the Qt plus 1, the output, next output of this circuit as 1. That is what the set condition is, the green one. And the red one is the reset condition, which brings, if C is 1, under that condition, if S is 0, R is 1, then no matter what the output was from the Q, it will become a 0. That's the reset condition. And other 0, 0 are the normal hold condition, as we have seen in case of S bar, R bar latch. But it is a little bit of negative logic. 1, 1 was hold. In this case, it is a positive logic sense, in that sense, so it becomes a 0, 0 is a hold condition. And that's why it is called a SR latch. It is no longer called an S bar R bar latch. This one is a S bar R bar latch because intuitively it's a little bit different operation, saying that if this terminal logic is 0 and this terminal logic is 1, it is a set condition. And then other way is the reset condition. So that's why it is called an S bar R bar latch. Whereas here its control is purely if set is 1, R is 0, then it's the set condition. If a set is 0, R is 1, it's the reset condition. So let's try to build that up and simulate and see what the behavior would be. So here I have the pre-existing code. S bar SR latch with Q bar R and C, and I have used two more extra input, preset and reset. So just so that we can ultimately build up our flip-flop, master slave flip-flop, and try that operation. But what is this extra? Extra are basically nothing but adding one more let me try to annotate quickly. So one more here and another here. So this becomes a 3-terminal NAND, and this is a preset, right? The 0. So this is preset is basically if it is 0, then it's 1, right? So this is my preset. And this is my reset. Okay, so that's the extra 2-terminal I have added in this component in the Verilog simulation model. So let's look at that. Okay, so we have similarly 4 instantiation, just like these circuit says, and connected. This control and S and R, exactly that wire connection is going on there. And we have a test bench for this, which is called SR Latch test bench. And there we try to simulate some of the condition like asynchronous preset, means presetting the queue to 1, no matter what the control value says, and then hold through the reset condition. Then we reset, then hold it, then set and hold it, then asynchronous reset. So these are the sequence of operation we'll see in our simulation. So let's open up that module then, SR Latch TB. Okay. Data flow wise, let me see if it can bring up. Yep, it can bring up. So there are 4 instantiation, and here is the feedback loop, one driving another. And we simulate. Where is my waveform window? There. So we are interested in all these. Let's not have the Q bar. It's, we all know Q bar will be inverse logic of the Q. So we add them. Okay. Right. Let's say a little bit rearrange. Reset goes there, C goes there. Okay. And simulate. Okay. Where is my simulation? Oh, there. Okay. All right, it end of the simulation, and let's look at our waveform. And just okay, I think this is a good view. And here, into flow. Now you see the preset is 0 at this point, and C is 0. Even if you put the C as 1, it won't matter there. You can try it out your own. But you see the Q value is 1. So this is a preset condition, asynchronous preset, where keeping preset to 0, reset to 1, we can actually control the outcome of Q logic from the entire circuit. And then we went to the hold condition at this point. So we are holding the data all together because the C is 0. C is 0, so that's a hold condition for us. So value does not change at all. Then we want to have, then at this point, we change the R value to 1, S value to 0, which is a reset condition in a normal way, means it would have brought down the Q to 0, but it is not bringing down Q to 0 because C is 0. So see, like that's what the control means. I am controlling the behavior of that internal S bar R bar latch, that even if the input, the overall input changes to an reset condition, it is not resetting because the control is blocking that logic to propagate their way into the S bar R bar latch. So that's why it is not changing. So C is 0. Now you see that at 15 nanosecond, I change it to 1. See, and immediately the logic value Q becomes 0 because it follows now that S bar, R bar logic, the internal latch logic, and it brings down with the S0, R1, it brings down the Q value to 0, it reset it. And then after at 20 nanosecond, I bring down the control signal to value 0. And during that time, I put the S to 1 and reset to 0. Normally, it would have set the Q value to 1. But since the control logic is 0 there, it is preventing it to do that. It's keeping the Q logic to be 0. Only when that control signal is raised to 1 at 25th nanosecond, your logic value outcome of the Q output become 1. And then it's holding onto that. And the end, I have shown you an asynchronous reset where I kept the preset as 1, reset at 0, and that brings down the value of the Q to 0 asynchronously. It doesn't matter what the C value is. I could have, well, I should have kept the C to 1 to demonstrate that, but anyway, you can do it yourself. And that's the concept of the latch with a control. Question? Okay, now let's move on to the next one, a D-latch, okay, where we actually eliminating these race condition 1, 1, 1, 1, so that our circuit, electronic circuit, become a little bit stable from the functional point of view. So this is the D-latch where it is basically tying up the SR with the inverter. And just one input called D, and D follows, our Q follows the D, logic of the D, as long as C is kept open with 1. So that's the whole logic. So let's look at that. And simulation, yes. And then okay, here's my D latch. So what I did is I actually instantiate all the NAND instance with that preset and reset everything, 4 of them. So 4 of them plus 1 inverter, that becomes it. But I could have also used an instantiation of SL latch. Okay, just I didn't do that, for example. But yeah, you can try that out. Instantiation of the SL latch itself there inside the D latch and make it a D latch. That can be done. So here is an instantiation of exactly of this circuit, with the exception of this final 2 NAND gate have a preset and reset, the third terminal, preset and reset. So that's for this one. And sequentially, we have one test bench for that. We test the asynchronous preset, hold. It's a similar thing, but as the previous one, but we are controlling the D instead of both S and R. It is just D we are setting up with one logic. It will follow the storing pattern will follow that logic as long as your C is 1. So let's see that. Let's simulate it. So it is an SD latch test bench. Okay. Let's add them to our web and data flow. Let's place it here. So here the 4 NAND instances and 1 inverter right there, just like this one. And we have the waveform right here. Let me rearrange, reset up, C up, okay, and simulate. Okay, end of the simulation. All right. So let's see what is going on. So preset 0, reset 1, that's a preset condition. So Q become 1 no matter what the C is. And then becomes a hold condition, preset reset to 1, 1, C is 0, and D is 0 here. See, in normal condition, Q would follow the D, but since the C is holding at 0, it is keeping that logic and preventing that to propagate to the Q output of this whole circuit. And that's why the Q is still holding on to the previously set value to 1. And it goes on, and 15 nanosecond, I open up that control, set the control to 1, D is 0, so it's now start following the value of the D. So it's 0. So as long as I'm changing the value of D, it will keep on Q will be keeping on changing. But let's say at some point of time we put C to 0 and D to 1, so it didn't follow that point. Q didn't follow, even if D is 1, but C is shut down at that moment to 0. So we close that gate at the moment, and Q remain at 0 till we make the C as 1 in the next time. And that's when the Q follows the D, it goes to 1, and then it goes down, and then at the end, it is basically an example of reset, asynchronous reset, where preset is 1, reset is 0, and that's what your Q is making 0 onto the output of that whole circuit. So that's the functionality of the D latch. Question? Now let's come to then this D flip-flop, and let's try to investigate the operation of the D flip-flop, and that is the important component that is used throughout in the microprocessor. So we have that, I have that simple code, simulation. Which is, here is a D flip-flop. It is Q, Q bar, D, and clock. Now we are basically saying that the C terminal as a clock terminal. So as long as we actually periodically change the logical value of the C, it's basically a regular clock signal. So we rename that C as a clock. Doesn't matter, we could have called it C. It really doesn't matter. It's just for a clarification purpose, that's a clock functionality. And then we have preset reset asynchronous, preset reset as an input, output QQ bar. Here we are actually doing this one, exactly this circuit, I believe. Let me see. Is okay. Master is driven by the clock C. Okay, yeah, exactly this one. And then the slave, the second part, the SR latch part, is driven by the clock part. So that's exactly the circuit we are doing. We're instantiating one D latch or one SR latch and combining them using the wires, intermediate wires, that master Q bar. So master Q here goes into the master. So this is master Q, and this is the master Q bar. So this one is connected to the S, and this one is connected to the R. So that's what is happening in this code. You see the S, that pin is driven by the master Q, and R is driven by the master Q bar, with the clock and clock C being driven by the inversion of the input clock, input C. So that's the clock bar. Reset goes as it is there. So this is the circuit, and let's try to simulate and try to see if we can understand the timing. On the test bench side, what we have? We have, okay, here's a little bit explanation needed. One thing you see that I have two instantiation. One is a D flip-flop, which is driven by a clock. And this clock being aware, and it's also an output of another logic entity. It's called clock generator. We name it a clock generator and we define it here. So this is the behavioral definition of the clock generator module, which we have defined some parameter. Let's say it's the frequency of 500 megahertz. That means my time period, I can calculate it with a real type value there. Time period is 1000 by the frequency, which is in the nanosecond. And then just like a regular module, I have an output clock and also register clock. It doesn't have an input. It's just driving out some clock pattern. And initially, we start at the simulation, beginning of the simulation with a logic 0. And always at half of the time period, logic invert itself. So it starts with a 0. After t by 2, it becomes 1. Another t by 2, it becomes 0. Another t by 2, it becomes 1. So that's a very simple behavior description of a clock generator. Always means like without any condition throughout the life cycle of this simulation, keep on doing this task, clock equal to inversion of the clock every t by 2 nanosecond. That's what it is defined. So that's the generation of the clock, and I'm feeding that clock into the D flip-flop instance with some register D preset reset driving in, and we are looking at the Q bar as an output or the definition of that. And then since I don't need to drive the clock anymore, it is generated from the clock generator, I just worry about the input D and preset reset. So just what I did, preset initial start, I preset I reset that. Reset 0, preset 1 means our Q becomes 0 with holding D to 0. And then at the second nanosecond, I did change that to the hold, okay, non-preset, non-reset signal, and then keep on changing the D at some certain time point, and let's see how it behaves. Question so far in this Verilog description? Okay, so let's look at that TFF test bench. Let's load it. Now let's look at that one. Okay. So I have the clocks. Let's see if I can expand. The driver. Okay, expand now to drivers. Okay, now it's getting complete. So how many NAND gate we are expecting? We're expecting to see 448 NAND gate total and 2 inverter. 1 2 inverter we have, which is expand through the reader. One, two, three, 4, 5, 6, 7. Okay, expand to the reader. So here is the feedback. Here is probably no. What else? Expand to the reader. Okay, did you have all this 1 2 3 4 1 2 3? Oh, here. Expand to the driver. Okay, 1, 2, 3, 4, 1, 2, 3, 4. Okay, we have all the gates there. Hopefully, yeah, 2 inverter. And our waveform, let's add it. D, C, preset, reset, Q. Add to the wave. Okay. And W1, W2, W3, maybe we can have them. Just hold on, let me see. Sequential logic D latch. No. Oh, wait a minute. What did I add? This is the master side, right? Okay. What I need to do is go there for the whole instance. Q. Okay, add 12. Okay, and also let's follow the master queue. Master queue and master queue bar. Okay, preset, reset, onto top, clock, onto top. Okay, we are ready. Simulate, and let's see what is happening here. Okay, first of all, you see the clock is every 5 nanosecond it is toggling this periodical signal, and we have the preset reset at that moment. So Q bar, Q becomes 0. Your output of the Q becomes 0, right? So, and this is the master side Q bar. Also Q is 0, Q bar is 1, and that is the reset condition for the S bar R bar, and that becomes your ultimately output of the DFF becomes your 0. Now, at this time point, I'm setting D as 1. Q is not following it. Okay, the Q is not following it yet. As soon as clock goes high, my Q start following the D. Okay, so whenever it is C is high, Q follows the D, and let me first remove them. It's not. Let's first concentrate on the Q output of the D flip-flop. And then when it goes down, okay, Q goes down, D is still up, my Q goes up there. Okay, so here's the behavior. So when it is up at this end, my D latch, master latch is activated. Well, that's why I brought up the Q of the master latch. Okay. Okay, now you see. Okay. So here, when C is up, master latch Q is changed, but not the slave, not the final output. It is not following that. So internally, this guy got changed at that point, and then as soon as the C goes down, by slave part registered that value. So previous point, this guy is holding up 1, and this is still 0 at this point. So the value 1 is not reflected at the high of the clock. But now, as soon as this clock signal goes to 0, this guy goes to 0, this transferred into here. So this output become 1 instead of 0. So that's what is happening also in this timing diagram. As soon as the clock goes down, your Q is following the D value at that point. It switch over at that point. And then Q goes down, it does not matter. But when the next up value comes, at that point, you see the D value is still low. So your master Q is following the D value during that entire high point. In this time, between this time period, your D gets changed, your D signal gets changed to high. That's why your master side Q is following that up, but not the slave side. Slave side is still sticking to that value, old value 1. And then it goes down, right? Clock goes down, D is at high, So that means effectively, it did not change the value 1 at all. It did not follow that 0. This 0 is not reflected back at the output of the slave side because of this logical and timing combination of this operation. And then some random D logic coming up and down and up and down. Whenever this C is on, your master side logic is exactly following the D logic. And whenever it is off, master side is just holding on to that last value. On the slave side, this one output characteristics is that if the D value is set before, if the D value is set, whatever it is set within that high period, it will follow that logic. You see, like during this high period, D ultimately stable at 0. So that's what the slave followed. During this period, D is stable at 1, right? It become 1, become 0, and then become high. Q followed that last condition. During this time frame, D was 0, then went to high. So that's what ultimately Q followed. And during this condition, D was kept high. So that's what is followed. Only in this time range, D was stable at 1, at 0, at that falling point, and that's what it captured there on that Q side. So that's the behavior of the flop you need to understand, and very clear, like what is this timing relation, how this data is actually going from D to the Q with respect to this clock signals toggling. Question? Okay, let's take 5-minute break. 8:25-ish, we'll be back. Okay, let's get back to our discussion. Just one quick closing remark on the previous discussion we were having is this. If we look at the characteristics of these flip-flop, D flip-flop, you see that the matter, like what matters at the final outcome is what the value of the D at the falling edge of the clock. So at the falling edge, if D is 1, Q is 1. At the falling edge, D is 1, Q is 1. This falling edge, D is 1, Q is 1. And this falling edge, D is 0, and that's Q is 0. So Q is following the D at the falling edge of this clock signal. And that's what we call it a negative edge triggered flip-flop. So it's a logic, Q logic is triggered at the when the clock logic goes from high to low, negative edge triggered. So if we change that into reverse that logic of the clock, like just an invert clock at the stage and then another inverter at the down, or you can do a separate configuration there, it becomes a positive edge triggered flip-flop. You may want to try that your own, and you'll see in that configuration, only if this goes to high, the Q follows the D at the point, the value of D at where the clock is going from low to high. This is the positive edge triggered flop. If you go with this connection internally in the circuit, it becomes a positive edge trigger. Q follows the D at the positive edge of the clock. All right, now let's do some pop quiz. Please go to your canvas and let me do the poll. If you are ready for the quiz password, pop quiz launch. Let me wait for everyone to get hold of that, become ready for password enter.
Yes, sir.
Yes?
Once the quiz is done, will we then be free to go?
Yeah.
All right. Thank you.
$38 of 42 said you are ready. 39, 40. Maybe I will just open up the password for you guys. Just hold on. This password. Try this. Okay, I think we have the quiz result. Apparently, average score is 76% with a high score of 100%. As a whole class, we need to work on that. Okay, maybe keep it up to 85%. That's my hope. Uh, Regarding the stat, the previous quiz one, as a whole class, the performance looks good. Passing rate is 94.6 and B minus or better is 91.1. Uh, like 34 of you got almost like around 50, and 45 to 50 is 34, and then 14 there, and there are a couple of odd apples there. 2 3, I think these 2 0 they are dropping off from this course, that's why they're not appearing here. That's why we have 2 zeros here, but overall that's good. This is good. Now what's coming up? Coming up is our next thing, sequential logic design and design components. This is another important uh, chapter to study on, and I believe this lecture 8, actually lecture 8 will continue for 2 days, like next day and also March 2, that day. So we can split it up. Like this is quite a big topic. You can see there are 7 different parts. So we'll split it up. We'll start with the sequential circuit design, the steps, and we'll go through a sample design. And then we can possibly quick review on the decoder and multiplexer. These are, we also taught it in our CS147 class, which whoever was my old student from that class, they're familiar with these two as well. These are very easy thing. So let's target for the next day, February 25th, to review these part 1, 2, 3, 4, and 5 till multiplexer. Let's make complete, and next day on the same lecture 8, we'll complete from the little bit complex part like register and the barrel shifter. These are 2 intense topic basically to be done with for this class, and this is pretty new for my old student as well. Uh, these are time consuming, as you see, like 26 minutes and 25 minutes. Those are big things and very complex ideas that I need to pick up. So let's focus on these 2, part 6 and part 7 for March 2 class. That means you have the weekend to go over this video and understand and pick up the concept. Before that, let's make sure we complete till part 5 and we're done with that. So our overall, we have these 2, sequential circuit design as a step, that topic, and digital circuit components, where we are actually trying to define, let me go to that section quickly, trying to define commonly used digital component to build up a microprocessor. So there are decoder and multiplexer. Those are 2 important, and you will see like in our processor design, we need to use multiplexer and left and right everywhere throughout in the processor implementation. And then we'll go with the register, the storage element. We start with this flip-flop concept and how we build up on top of that at a register, 1-bit register. From that, how can we make a multi-bit register? Remember the register in the assembly language, you were used to program a register. We're talking about that register, how this structure is done inside electronically inside this processor. We will talk about the shift register. We'll talk about more complex control over the shift register, like left shift, right shift, how we can make it together into one component, complex circuitry. And from there, we will go with the combinational shifting. That's a very intense concept that how we can avoid sequential circuit, which is essentially a slower than a combinational shift circuit. That concept is very crucial. we'll pick up on that on the next day. So this is all for our study, for upcoming study for next 2 days. Lecture 8, 2 days. It's not 1 day studies. It's consecutive 2 days we'll spend on the lecture 8 to grasp the critical concept of the components. Question?
When will you be unlocking the quiz results?
Oh, okay. I'll do it by tonight. Quiz 1 I have. Oh, means Bob quiz, right? You mean Yorick?
Yes.
Yeah, by tonight. Yeah, tonight
Okay, thank you.
I'll open that. Yeah.
All right, have a good night.
All right, then we'll stop tonight if we don't have any other question. And then we'll see you on Thursday. Remember tonight to your project 1 submission.